This is the second part of Lesson 26 in Heat Transfer. In Lesson 26, we will discuss thermal radiation heat transfer in a large isothermal enclosure. The concept of a large isothermal enclosure is a critical one when analyzing thermal radiation heat transfer problems, including that of the concentrated solar receiver wall. In this part of the lesson, we will describe what the net radiative flux is on a surface that is situated in a large isothermal enclosure. By the end of this lesson, you should be able to explain why the large isothermal enclosure assumption is so beneficial in the analysis of thermal radiation heat transfer problems. You should be able to calculate the irradiation on a surface that is sitting in a large isothermal enclosure. And you should be able to define what the net radiative flux is on a surface. On with the lesson.
90% of radiation problems, including this one, we can handle with this equation that I've already shown you, which gives us the net radiative flux. And it's epsilon sigma Ts to the fourth minus T surroundings to the fourth. And I think when I showed this to you at the beginning of the class, I said, there's so much going on inside of this equation. I'm going to show it to you because the book gives it to you, but we really want to start to unpack this now and understand where does this equation come from. In order to apply it, right, we had two important assumptions, and one of them is that the surface of interest is sitting in a large isothermal enclosure. Actually, I don't know why I put the flat up. You don't need that. Sitting in a large isothermal enclosure. So the picture that I often think of when I think of that, and you can imagine, say, a piece of the wall of the receiver, okay, is sitting here. And if you think about all of the space, right, around it, the environment around the receiver, you can kind of imagine a hemisphere. And the walls of the hemisphere are at the temperature of the environment, basically, right? So that's what we call the surroundings temperature. So don't think right now, kind of put the concentrated radiation out of the picture of this, and just imagine, like, if you want, imagine that a cloud is rolled by, and so the sunlight, concentrated sunlight's gone away, and all we have left over is a hot receiver surface now. There's still radiation happening, right? Because the receiver surface is still emitting energy, right? So there is some emission. And the complicated part of this is that there's also the surroundings, and the surroundings has a temperature, and all of the surroundings, because it has a temperature, is also emitting radiation. And so there is some incident radiation on the surface, and the question is, what is it? Like, how can I quantify it? This is, in a lot of ways, what makes radiation so challenging, and what we have to spend a lot of time talking about is really dealing with this incident radiation. So imagine, to try to give you a sense of why this is complicated. Imagine that I wanted to calculate the temperature of the surface of my phone in this room. So the temperature that it comes to is going to be dependent, of course, on the temperature of my phone, because my phone is emitting radiation, right, in all directions right now. It's also going to depend on, like, what's incident on the phone, right? Like, the back wall has a temperature, this wall has a temperature, Aaron has a temperature, I have a temperature, and all of these surfaces that have temperatures are emitting radiation, which is coming over and striking my phone. And some of that radiation is being absorbed by my phone. But in order to predict, right, what's ultimately absorbed, I have to know what's striking it, right? Like, I have to know what's there. But knowing what's there means I have to know also what the temperature of the back wall is, what Aaron's temperature is, and what my temperature is, and what the temperature of that wall is. But the temperature of that wall also depends on the temperature of my phone because my phone is emitting over there as well. And of course, I have to work out the problem on that wall then. What's incident on that wall? So I can look at the balance between what's being absorbed versus what's being emitted back. So you see every surface now potentially becomes coupled together because what's happening on this wall also depends on what's happening on that wall and what's happening on that wall, and what's happening on the surface of my phone. So it can get really, really complicated, right? Does that make sense? Like everything gets coupled together in radiation. Every possible surface is coupled together because what happens at any one surface depends on what's happening in all of the other surfaces and potentially on that surface itself, because it's possible in some cases where you emit energy and the emitted energy from that surface reflects and comes right back. So it's super complicated and coupled together. So the question is, what basically this assumption simplifies that down, right? We're able to take this super complicated problem and simplify it down into a statement that the incident energy on the surface is equal to sigma times T surroundings to the fourth. Right? That's what this statement gives us. It gives us this substitution. And we can make that substitution. It doesn't matter what the nature of the other surfaces are, so long as the surroundings are isothermal and large relative to the surface of interest, we get to make that substitution for the incident energy, which allows us to look at the balance and actually get an equation. Right? So in the end, what I want to know is what's called the net radiative flux. It's going to be the net radiative load on the receiver surface, and it is what's ever emitted minus what's absorbed. Okay, so the emitted stuff is given by the Stefan-Boltzmann law and the property of the surface called the emissivity. So we haven't like really unpacked what the emissivity is, but I think I've given you enough to know that it's the thing that compares it to, right? This is the black body, what a black body would be emitting at the surface temperature Ts to the fourth. So when I multiply it by an emissivity between 0 and 1, I get the actual emission from the surface, which is less than that of a black body because no surface can emit more than a black body can. So that's the emitted part. And the absorbed part is given by the absorptivity times whatever is incident. Right? So this is the absorptivity. But now we can make a substitution for the incident stuff. It's sigma T surroundings to the fourth. And if we say that the emissivity is equal to the absorptivity, which is true for a diffuse and gray surface, then that becomes this equation. You see that? So this equation works, right? Anytime we have a large isothermal enclosure, because that allows us to make this substitution for G, and when you have a diffuse and gray surface, which allows us to say that the emissivity is equal to the absorptivity. So I want to convince you of the first assumption, and then on Monday we'll talk about what a diffuse and gray surface is, right? And when we get to make this this assumption that epsilon is equal to alpha, and when we won't be able to, because there'll be situations where we can't. But this is the big one, okay? Because it takes, and hopefully I've tried to convince you, right? It takes a super complicated problem and it makes it really, really simple.